Hey, so hi, welcome. Today we have a very special guest. We have a theoretical physicist, Sašo Grozdanov. Sašo Grozdanov is a researcher at the University of Ljubljana and the University of Edinburgh. He works in very cool stuff like string theory, black holes, quantum chaos, which are topics that I don't know. I know very little about. So for me, it's actually very exciting to have the opportunity also to learn about these topics. So hi, welcome.
Hi, thank you. Thanks very much for having me.
Okay, how are you? Everything all right?
Yeah, thank you.
Okay, good. So I'll start directly with the questions. Even though I have studied physics for already more than 10 years, I gotta say that one of the topics that I still find a bit intimidating or very intimidating is string theory. So first of all, what is your best definition about what is string theory?
Well, it's already this question is quite difficult, and yes, it is a rather intimidating subject, mainly because we don't really know what it is. I would say that's one of the problems. So, I mean, string theory, one can define it in the sense of, well, it's a quantum theory of little strings. So you say, instead of taking particles, you take your little strings, you treat them quantum mechanically, and you do something with it that's consistent with quantum mechanics, it's consistent with relativity, and, it's a wonderful subject. Out of it come, very many wonderful things like quantum gravity. But what it is fundamentally, the more we've learned about string theory through decades, the more clear it's become that it's not only a theory of strings, it's also a theory of these extended, larger, higher dimensional objects called branes. It's a theory of quantum gravity, but in some cases gravity is just quantum field theory, just basically, quantum mechanics. So we don't have a full definition of string theory, I would say. We kind of, it's a massive subject. It's a sort of an umbrella term of various ideas that are consistent with quantum mechanics and gravity. And we understand some corners of it. Okay. And the corner from which this started was from strings, and strings are these one-dimensional objects. They can be either straight or sort of curled up, closed or open strings, they're called. And sort of, this is called sort of a perturbative approach. It's kind of the easiest approach to understand. And this is how it started. And so, it is a theory of these essentially strings, but as I said, in this massive landscape of this theory, which we're not quite fully able to define or even know what exactly it is, or how to write it down. There are a lot of unanswered questions. So it by itself, it's a rather difficult question to answer. But for the historical purposes, we can think of it as a theory where you start with instead of particles that move in space-time, you start with little strings, which are higher dimensional objects, and they vibrate. Their vibrations give rise to excitations, which are then interpreted as particles with different masses, and so on and so forth. Okay, so that's kind of in some way a definition of string theory.
That was a general idea.
Yeah.
And I guess maybe to give a context, like sometimes I don't know, quantum field theory, in other theories we have like point-like particles, and then in string theory you pass from point-like particles to these objects that you call strings, and I guess that gives you some different possibilities or some different formulation.
Yes, yeah, the theory is much richer. It has, one of the reasons I think why people historically got very excited about this is because it did give rise to, a tower of particles, and somehow by accident, it just so happens that, the particle that is very naturally described is a graviton, which is it's a massless spin 2 particle in the jargon of particle physics. So of course, because there's this old historic problem of how do we combine gravity with quantum mechanics, well, string theory just naturally does it. Okay, so there are very natural reasons why for decades people have been excited about this because it does manage to combine these two subjects one can combine them in a variety of ways. This does it in a way that's kind of consistent and one can actually do something with.
Okay, I see. So yeah, you will see like one of the main motivations for string theory is precisely this idea about the unificating or the uniting these four fundamental forces. And apparently within the framework of string theory, there seems to be some reasons to think that maybe someday it should be possible.
That's right, yeah. So if I say a little bit more about this, right? So what we actually know is that we have, we usually say 4 fundamental forces in nature. So one is the force of electricity and magnetism, which is combined into one, and this is called the theory of electromagnetism. This goes back to Maxwell. Then we have two nuclear forces, which are responsible for things like nuclear decays, stability of atoms, various things like this. These are the weak nuclear force and the strong nuclear force. And then of course the idea is to somehow combine all these things into one overarching force, let's say. So the electromagnetic force and the weak force are very nicely merged together into what is called the electroweak theory. This is, the basis of the standard model of particle physics, which is an extremely successful theory with, millions of predictions, millions of measurable things that people do at CERN and other colliders, and this is extremely successful. So then, then there's this strong nuclear force, and using kind of similar mathematical tools, you can combine now the strong and the weak and the electromagnetic force into one thing. This is called the grand unified theory. It's a consistent theory that makes predictions, but none of these predictions have been verified. So this is not a particularly successful thing. Well, it's mathematically, conceptually successful, but the various typical predictions that what is called grand unification makes, for example, decay of the proton, these things have not been experimentally observed. So this is kind of experimentally, this part of unification is experimentally problematic. Conceptually, it's not problematic. And then the fourth force is gravity. Okay. And so somehow then merging all of this together becomes also conceptually very problematic, because if you just naively treat even just quantizing gravity, even treating it as a quantum mechanical force, the way you can treat all of the other forces is in a sense useless. You can't actually calculate anything. I mean, you can calculate some very, very limited things, but the quantum theory in itself, if you were to treat it as a full quantum theory, it will just give you nonsensical infinite answers for essentially every question that you ask. And it's very hard to make any, sensible finite prediction. Because at the end of the day, you would like to calculate something and you would like this calculation to give you a number, right? I don't know, 7. Yes. Whereas, this naive way of doing quantum gravity will just every time give you an infinity and infinity and infinity, one that you cannot regulate. We use this word regulator or renormalization. Okay. No, this theory is called non-renormalizable. So then somehow, even this is not very good. So then somehow the idea of unification of all of these forces, which should all be quantum, we strongly believe. Okay, that I should say, I guess that's also a belief in some sense. Because as far as I know, we don't have any direct measurements of quantum gravity being really quantum. But I mean, somehow, in the mainstream of physics, and there are very good reasons for this, nobody, I think, really doubts that gravity should also be a quantum mechanical phenomenon. Anyway, so this doesn't work, okay? It doesn't work for technical reasons. And then string theory just somehow magically resolves all these problems. It's able to make quantum gravity a consistent theory. It also includes various other forces. The problem with string theory is that it's very hard to get the exact thing that actually exists in our universe. I mean, we've not been successful at this particularly. Or, I mean, okay, there are ways of making some parts of this work. So you can get things that look like electromagnetism, weak, strong forces, things like this. Up somewhere there's also gravity. But typically you also get a very large amount of other things. So you won't have only 4 forces. Typically you'll have also other forces. You have these towers of particles. There are lots of predictions that any of these string theory models make. And the problem is that, even though the formalism is consistent, it gives some predictions for every version that you choose. It will, none of this has been measured. So that's kind of one of the problems at the moment, or usually the criticisms of the theory.
Okay, I see. Yeah. And you mentioned that apparently you can have predictions from other forces. Can you maybe give an example of like what kind of force will you have in a theoretical calculation, or I don't know, or is it?
Not a very specific example. I mean, these are just basically, other forces. They're like strong nuclear force, let's say. There's some carriers of the force. They have some property. There's some number of them. I don't think that I can give you anything particularly specific I'm not aware of any particularly interesting prediction that these other forces would make. But I should also say that this is not something that I work on.
Okay.
So this is the field of this I would call string phenomenology, and that's the attempt to make string theory really work for exactly the kind of particles that we have in our universe. And then exactly discover what are the other particles, what are the other forces. So I don't work on this. So, people who are really experts of this would probably be able to answer this question better than me.
Okay, no, but it's good. And now you gave us the big picture of string theory, so to say. But because I was reading, apparently it's a very wide framework. It's not only one thing really, in the sense that there are many, within string theory, there are many sub-areas, of fields. So maybe you could talk to us more specifically about how do you use string theory or about your research?
Yeah, so I am very interested in string theory as a kind of so it's as you said, it's a kind of an umbrella of theoretical ideas. They're these extremely powerful ideas. They're all nicely consistent with gravity, so relativity, and quantum mechanics. So it's a healthy thing to use, because it follows the right principles that we believe that physics follows. And so what string theory has taught us, that there are these various bizarre, unexpected connections, okay? Because once you've managed to write down a theory that knows about quantum mechanics, that knows about gravity, you can hope to find unexpected connections in this language through the formalism, the mathematical formalism. And this is exactly, one of the aspects of this that came from string theory. These ideas are called holographic duality. So it's an idea that in some sense gravity is a holographic theory. What we mean by holographic theory is that in a sense, so this didn't used to be particularly precise. So in a sense, gravity works as if the quantum mechanical nature of it had one less dimension. So this comes from the discussion of black holes a few decades ago. It goes back to understanding what is the entropy of a black hole. So, entropy you can think of as a kind of a measure of information.
Okay.
If you go back to Boltzmann, to statistical mechanics, the entropy of something will tell you how many microstates there are available for what this physical system can be in. So if you ask yourself, what is the entropy of a black hole? Right. So black holes are these sort of most extreme, and in other cases, other sense, the simplest kind of objects that we have. And now we're also very, very sure that they actually exist. So these, black holes are rather fascinating. Mm-hmm. And you can ask yourself, what is the entropy of a black hole? How much information does it in principle contain? And one of these surprising results that came from gravity, more or less classical gravity with some aspects of a little bit of quantum mechanics mixed into it, is that the entropy of a black hole is proportional. So you can think of a black hole as a sort of a ball, right? It's a ball, and the surface of this ball, let's call it, this is called the event horizon. Okay. So it's black in the sense that nothing can ever escape it. Okay, so no light, no particle classically ever escapes this event horizon. And this event horizon, it's like a surface of a ball. You can calculate the area. This is very easy to do. You just calculate the area of this event horizon. And it turns out that the entropy, which contains which amounts for all the information inside the ball, is proportional to the area of the event horizon. So the inside of the ball is three-dimensional. So, naively, one might have imagined, of course, that somehow the amount of information would scale with the volume of the black hole, but this does not happen. It scales with the area of the event horizon. And the area is two-dimensional, right? So it's one, you can cover it by a sheet of paper, and a point, let's say, to be precise. But this is a two-dimensional surface.
Okay.
So black holes, the amount of information is proportional to one less dimension. And actually, what is even more fascinating is the fact that we also, there are arguments to be made that no volume of anything, so no volume can ever have more information than a black hole. So the amount of entropy inside a black hole is actually the maximal amount of entropy you can have in a volume of that size. So, so there's gravity, and all of a sudden now the information of that looks like it's kind of living on the surface. So there's a dimensional reduction. And this is why we use this word holography, because historically holography came from optics, I think. So a hologram in optics, right, is this, it's essentially a picture which contains some information about 3 dimensions. So it's a 2-dimensional surface. It's like a photo, but it's a photo of something. And if you look at it from different angles, so people, for example, undergraduates who do physics lab, often they will do this in a physics lab. It's one of the most memorable ones for me, actually. You take a picture of some coin or something like this, and when you look at it from the sides, you will actually see 3 dimensions. It contains information about the whole space. Whereas a normal photograph is just a projection of 3D onto a surface.
Okay.
So that's where the name comes from, holography. Anyway, so long story, not short, but
but it's very interesting.
Semi-short. Gravity is believed to behave like something that has 1 less dimension, and this was believed before. And but the problem was that there was no very specific, precise way of doing this, of really understanding what exactly this means.
Okay.
So only through string theory were people able to make this very precise. So this was, in my opinion, of course, I'm biased because, well, I work on this because it is my opinion that this is the most interesting. So it's circular logic. So I think that this is the biggest success of string theory, was to understand in some types of quantum gravity what this actually means. So this goes kind of back to I guess in the 80s. In the 90s. Yeah. People were trying to understand the entropy of a black hole, and there was a very very important paper by two authors in the US, Strominger and Waffa, and they were able to calculate the entropy of some kind of a black hole that exists in string theory. It doesn't exist in our universe, but it's something, it's like a black hole. It's a black hole of sorts. And they were able to actually calculate the entropy of this thing and verify that this area thing was correct. Okay? They were actually able to count the number of microstates of such a black hole and compute it in 2 ways. Once from the area of this event horizon, the second time by the usual counting, and it matched. So, basically then people were studying these types of black holes and so on. So then there was a huge breakthrough in this that goes to Juan Malacena, who was able to find a very precise formulation of what is now called the AdS CFT duality or gauge gravity duality holography. And it's a very, very precise, very mathematical conjecture, incarnation of this holographic principle. Okay, so basically from that point on, it kind of became rather clear, at least for some types of gravitational systems, for some types of black holes. When I say some types, these are special types of black holes that have what is called a negative cosmological constant. Okay. So if you go far away from such a black hole, the space looks rather different to what it looks like in our universe. So our universe is kind of flat far away, not really actually, because we live in a space that's accelerating, right? So our universe is accelerating, and that's synonymous with having a positive cosmological constant. This is, if you've heard of this is the problem of dark energy, for example. Well, anyway, so we don't understand quantum gravity in such spaces very well, but through this holographic duality, AdS CFT, we understand quite well what is going on with quantum gravity in spaces that have a negative cosmological constant. Okay. So these spaces look more like closed spaces, like there's a boundary to the space. And one can really, with this AdS CFT correspondence, one can really get to the heart of these various things, and you can ask very precise questions. And what you find is that quantum gravity indeed, works like something that has fewer dimensions. Okay. And this thing that has fewer dimensions is a quantum theory. It's a quantum field theory that doesn't have any gravity. So there's a precise duality between quantum gravity in some spaces and essentially quantum mechanics, quantum field theory, with no gravity in fewer dimensions. Okay?
Okay.
So, for example, now once you have such a precise thing, you can ask a question about, let's say, gravity, classical quantum gravity. We're also not so good at doing quantum gravity yet in the context of this correspondence, but let's just say gravity. You can ask certain very precise questions in 4-dimensional gravity or 5-dimensional gravity. And then instead of doing the calculation there, you can do the calculation in the quantum theory that has one less dimension.
Okay.
And actually, for what I do, for most of the things that I do, I am actually interested in the quantum theory that has fewer dimensions. Because that's one way of using this duality. So duality means that basically, whichever question you ask in one, there's a corresponding question in the other, and there's a map between the answers.
Okay. And I don't know, could it happen that maybe in one area or in one of these dualities, could it happen that it's easier to answer one question,
Yes.
and then you can make the connection in the other,
That's right.
let's
That's
say,
exactly
in the
what
other
happens.
space or in the other, I don't know, the other duality, so to
Yes,
say?
that's exactly what happens. So
Okay.
so this duality is what we call a strong-weak duality.
Okay.
So to explain this, so basically, usually in physics, right, we're not very good at solving anything unless the system is free in some sense. So, for example, we solve things that have, let's say, no forces, no interactions, and we can solve this exactly. And then what we normally do is we build small corrections to this result in corrections around, like, imagining that you have small interaction between inside of the system, okay? So that the constituents of the system are interacting weakly with each other.
Okay.
That's a typical way of solving any quantum mechanical system, quantum field theory. So let's say now you're actually interested in questions where this interaction is not weak between the particles, but it's actually strong, right? So what do you do? Well, not much, actually. You can't actually do very much. One thing you can do, and people have done successfully, is you put it on the computer, and you try to just solve it on the computer. And this has been successful for certain types of questions, but not other types of questions. So it's very hard to extract anything useful, for example, about time evolution of, let's say, we're slowly getting into these kind of like collective states. So, imagine that you have some liquid. This liquid is made of little particles that are interacting very strongly. And you would like to know, how this behaves through time. You do something to it, it evolves in time. So if these things are strongly interacting, you can't really do anything. So, it's very, very hard to solve anything. So now, actually what happens through this duality is that now some questions about strongly interacting systems in quantum mechanics, in quantum field theory, with no gravity at all, can be translated into complementary questions about black holes, let's say. And these, the translation works in such a way that these very difficult questions with very strong interactions are translated into rather simple classical questions with very weak interactions. Okay, there's gravity, but you can just solve this. Okay, you solve it, you get some answer, and then you translate the answer back into, whatever you were searching. So for example, you're interested in how quantum chaos behaves in such a strongly interacting soup of particles. You're interested in, when this thing will thermalize, how, for example, precise questions about how it behaves as a fluid, what is the viscosity of this thing. You can translate all these kinds of questions into some complementary question to do with a black hole. For example, you take a black hole, you kick it, and you see how this black hole relaxes back to itself, and you can calculate how this relaxation happens. These are the kind of typical calculations that we do, and then you translate these answers into something about the fluid that's made of strongly interacting quantum particles. So it's a very appealing aspect of this that I am very interested in. One can sort of turn this around and then try to ask something about quantum gravity that it's, sort of very difficult to even define. It would be even very difficult to say what that means. And that, through this duality, then again, you have some picture of this in quantum mechanics that you can try to answer. So, there's been a lot of progress, for example, in understanding gravity from the point of view of quantum information concepts in quantum mechanics and translating all these things from one to another, entropies, entanglement entropy, error correcting codes, various things like this. So, this duality works in a very nice complementary way. Usually when you can answer one question on one side, you can't do it on the other side, and then you just translate from one to another. And that's why these dualities, any kind of duality in physics, is usually extremely powerful.
Okay.
So that's kind of the aspect of string theory that I have found most fascinating. And it goes slightly away from this question of, is it the correct theory of our universe? To which the answer, we don't know. Probably whatever the final theory of the universe is will have some aspects of string theory as we now understand it. But exactly in what incarnation, nobody can tell you. We just don't know. Okay. But regardless of this, whether this is, regardless of whether the string theory that you now find in a textbook by let's say, Polchinski, whether this is the final theory of the universe, for practical purposes, for many people in my field who maybe would call themselves string theorists, maybe even not, it's not even clear who is nowadays a string theorist or not, what we have just learned from this, wealth of techniques are new connections between quantum mechanics and gravity. And, we have more than that, we have very, very precise models with which we can play. And once you have very precise toy models, okay, the black hole doesn't exist in our universe, but so what? You can still learn amazing things about it and see how all these various things work. And that's, I would say that that's where a lot of the field is at the moment.
Okay. No, but I find it very cool because even though these ideas, to some degree, they do sound very abstract, like they actually, I was talking with Tomasz a bit, and he told me that apparently many of these ideas about black holes, entropy, information, they actually have inspired a lot of scientists in the area of quantum information, for example. So,
That's
right. Even though they sound very abstract, it sounds like something that, I don't know, it doesn't, not necessarily, not that it's important to have an application, but I think it's very interesting that these ideas, they do have an impact on the physics community, not only within string theory, but they actually affect particularly quantum information, I would say, but I don't know what's your opinion.
Yeah, that's right. I think, it's exactly right. And it's because we have, from string theory, derived a new way of looking at old problems. Mm-hmm. And as soon as you have a new way of looking at something, it usually tells you something useful. Mm-hmm. And from string theory, from gravity, we have these, toy models with which we can play. And we can actually calculate stuff which you couldn't do in any other way using normal techniques. And so there was a sort of a revolution, mini revolution, or maybe not even so mini, in the field that was sparked from the work of, it was Kitaev and then Schenker, Stanford, Maldacena, Susskind. They understood how quantum chaos can be translated in this language of duality. And this was also something that I've been very interested in, for example, in how quantum chaos, that you can understand it this way, and these, some of these quantum information concepts then make their way into the dynamics of the whole system, the hydrodynamic expansion, various things like this. And, this is also why with Tomasz Prosen, your previous co-speaker in this podcast, we've been able to actually have productive conversations and work together on certain things. Even though he would come from a very different sort of background, someone comes from high energy physics, someone comes from, let's say, statistical physics, condensed matter. The nice thing about string theory, I would say, in the last decades, or 2 decades, let's say, has been that I think it's really managed to connect these various ideas together. And maybe that's even the biggest success of string theory, that it brought together people from various subfields of condensed matter physics, high energy physics, quantum information, and build some bridge in terms of a common language. And I think this has been very productive.
Okay.
Yeah.
Okay, very cool. Yeah, no, obviously I don't know much about it, but I find very interesting in all this, the fact that, yes, you can inspire so many ideas with quantum information. And also, to be honest, I think, from what you say, I have the impression that in the most, let's say, extreme scenarios, or scenarios where you have gravitational effects and also quantum effects, like black holes, or maybe the beginning of the universe, things like that. in the very, very big important questions, that's when string theory comes in. So I find very fascinating that it has all these, it has like the most, let's say, very important or very grandiose scenarios, but also it has inspired like some very grounded ideas in quantum information. So I mean,
exactly. Yeah. So I agree with you. Yeah.
Okay.
So even if nobody can tell you the final definition of what is string theory, let's not even get into that. No one can even tell. No one can even tell you what is the precise definition of quantum field theory. But okay, that's it's a question for a separate podcast. But even though it gave us very nice workable examples that I believe are close enough to reality that we can learn a massive amount from. At the end of the day, when you do material science, those are also very dirty models. And for example, in condensed matter physics, in statistical physics, you build simplified models of that, and you learn a lot from them. Even though they're not the exact replica of the actual system. Actual systems are always extremely difficult, very messy. But still, we've managed to do a lot this way.
Okay. So yeah, you mentioned some of the research that is on string theory, some of maybe what it makes it the most interesting. But let's talk about the problems, because I guess it's not everything is perfect. I will guess. So, for example, I mean, from what I read, is that a lot of the polemic or the controversial aspects is precisely that the fact that maybe many of these results don't seem to have like an experimental confirmation. So I don't know what will be your opinion about, because I mean some people even argue that it's a bit controversial to actually call it science, in the sense that normally one associates science to experimental results. But what is your opinion?
Well, I mean my opinion is that it's true. It's true that we don't have any precise measurable predictions of string theory. This is certainly true. But it's also true that every string theorist is aware of this problem. And if they could, they would. And if anyone could do better, they would do better. But we can't. Okay. So this is where we are. We try our best. Everyone tries their best. If there was an alternative approach that could provide some prediction, that would be great. There isn't, not as far as I know. But it's true. We should be aware of these criticisms, because fine, one has to be honest about the state of affairs. I agree. And people are aware of it. And that's why, that's the state of the field. Then there's the state of scientists. Of course, I find often the criticism of string theory is more related to the people in string theory than the actual subject. Because usually anyhow, who can really, it's very hard to criticize, it's hard to honestly criticize something you don't understand. Okay. And okay, fine, you can say there's no experimental prediction, very bad, we all agree. But often I think what is also criticism is that the field was oversold, that it promised to solve all the problems, that the mass of the electron would be calculated within, I don't know, a few years. I don't know when this was promised, probably before I was born. And I think that's also true. But these are psychological problems of scientists. The way science works, you have to, it's very hard to ever get a job or any kind of funding if you don't promise something. That's unfortunately just the way the system works. But people are aware of this, and these are problems, as we said, and people are trying to address them. And I think, I don't know if anyone is today calculating the mass of an electron. Maybe people are still trying. It would be nice, of course, that would be a huge revolution. But, I think there's been a sort of a step back and said, okay, well, we've learned a lot. We know something. We have toy models. It may be the final theory of everything. We don't know. Maybe not. Probably not, right? Probably there will be some aspect of this that we have so far overlooked. Who knows? And, we use it the best we can. We use it to learn about other things. We use it to learn about itself. There are many people. Within high energy theory, it's still a fairly large field. People are working on different aspects of it. But, I can, assure the viewers or the listeners that people are aware of these criticisms. Okay. And that, that they would like, that they are being addressed. And if anyone could do better, they would. Okay. Now, when you say if this is science or not, Well, I don't know. I mean, it's a question. I often think, I mean, of course, people will often say physics is an experimental science. And, that's nice. Yes, of course. Ideally, you make a prediction, you go to your lab and you measure it. Then what you can say is, of course, well, sometimes it takes a long time. The length of time is undetermined in advance. So you don't know, right? You can predict the Higgs boson. It will take 50 years and it will be seen. Or you can predict a particle that has mass very close to the Planck mass, and it may take millions of years to see. I mean, who knows, right? Mm-hmm. This is unknown. I mean, I think there always has to be space for this kind of fundamental science where you're not pressed to present a measurable result tomorrow. So okay, fine. So string theory can certainly make many predictions. If anything, the problem is that it makes too many predictions, and we don't know which one of those is right. Okay. So that if anything, that's its problem. And the question is, which one is the unique prediction? That we have no idea. So it's the uniqueness of the prediction that's really a problem. And then you could say, well, but maybe physics is also just a study of the fundamental laws of nature. What if some of those things simply aren't experimentally measurable? There are various ideas out there, which, I mean, you can call them non-scientific, I don't know, but it could be that there are many universes. It could be that the laws of, that the mass of the electron is slightly different in all of those. We just happen to be in one of them. Why we're in that one, we may never know. We may know some, this is simply not known. So what I'm trying to say is that I think there's certainly a not unlikely realm of possibility that there are certain things which are fundamental to our understanding of the fundamental laws, which are simply not measurable. Mm-hmm. As soon as you have relativity, for example, it gives you limits on how much you can know. For example, the fundamental aspect of relativity is that the speed of light is constant. All right. Okay. So, very simple thing here. So, the distances in your space-time in the early universe can grow much, much, much faster than the speed of light. That simply means that your knowledge of, even in principle, ever being able to access any part of that space-time is getting more and more and more limited. And this is exactly what's happening in our universe. Our universe seems to be, expanding very rapidly. So that means that, what we have contact with is shrinking because these particles are going further and further away. So we're in the future we'll be, exposed to less and less of it because they'll be outside of our horizon. And, there are certain things which we just cannot access. It could be, I think, if it comes down to the question of many universes, what are the masses of electrons in these various universes? Is this important to understand, everything? I don't know. It could be that in principle this is not knowable because you will never be able to go to those universes and try that out. And, and for example, I don't know, do a statistical sampling of different masses of electrons. I'm now, talking randomly, but I think that we should be aware that, having access to experiment is a luxury, perhaps. It's a luxury, and it has spoiled us in the last centuries. Things have worked amazingly. Quantum mechanics has been incredibly successful. Relativity has been incredibly successful. And right now we're in a sort of, stage of affairs where theories work very well. We have conceptual problems which are very difficult, extremely hard to solve. You can come up with many different solutions, but there's just no way of telling them apart. And hopefully, the ideal case scenario would be that out of all these string theories, whatever this is, there is some dynamical mechanism which selects out the unique solution. And, that's the unique solution for everything, for all the masses of particles, for all the charges, for all the forces. It's the unique solution for some reason. And, basically the entire universe plus other universes, whatever, let's call it the multiverse, they'll have these same laws and, that's fine. It could be that that's that. And then really everything would be fully predictive. It would be nice. But we don't know. I think there's a realm of possibility where this just isn't like this. I mean, I hope it's not like that. But so I would rather define physics as a, something that tries to find the laws of nature. And, ideally, of course, everyone is very happy if this is experimentally measurable. But we'll see. I don't know. I think we simply don't know at this point.
Yeah, but this problem of experiments, and you say it, but to some degree, not only limits itself to string theory, because I think one of the big problems in science is that experiments every time they become more complex and more expensive. And I don't know, back in the day, you had Faraday who had a laboratory in his garage, and you cannot do that now. Every big experiment and the Large Hadron Collider. How many millions of euros that costs? And I'm not saying that it's what you could argue that it's important. It's so nice that they have built it, but it's not easy. And you cannot build one whenever you want, or let's make it bigger. There's are very big investments.
It's a massive investment of money, which okay, fine. So there are other things that people spend money on. It's also a massive investment of time. Mm-hmm. Thousands of people, experts, experimentalists, engineers, people who have incredible expertise in building these things, which I could never do. So I'm a theoretical physicist. What would I do if I'm placed inside of CERN? Nothing. Absolutely nothing. I probably wouldn't even know how to turn on the lights. So, I can even there's this enormous machinery of people who are all working together, and what they've achieved is spectacular. But yes, it's getting harder and harder. Absolutely. You can just see this by the number of people that you need, and the amount of time it takes, and how much money it's costing. And so I don't know how far this can go. It's unclear at the moment. Then as soon as this becomes a problem, as soon as this becomes a fact, then this becomes a problem of society. It becomes a problem of politics, of the economy, and then it's not only up to string theorists saying, well, we believe that supersymmetry exists, and therefore you will find a particle there. It becomes the whole society becomes involved, and it's very difficult. So I don't know. Okay. It's unclear what will happen. They could decide to stop funding this, which I think would be a huge mistake, because we don't have any other approaches. Except building a bigger collider. I don't see any other approaches to really, going up in the frontier of masses of energies. But who knows? I hope that they will build something bigger at CERN. Yeah.
Okay.
Simply because I don't know what else they could do.
No, nevertheless, I do think it's very important, and it's very fascinating that we still attempt to answer the really important questions, the fundamental questions. And I think in that aspect, string theory, one has to recognize that it attempts, at least it attempts, and maybe it's our best attempt until now, at least, to understand these very fundamental problems.
Yeah, I would agree. Yeah, and we've learned a lot, even if we've learned a lot about things just by doing it, even about other things. And I think it's certainly been a worthwhile endeavor. And people will keep doing it because, it's a kind of a natural place to go from gravity and from relativity, which we understand very well, and they've been very successful. And it's a kind of a natural completion of these things. And one of the things that I think is very important to remember is that there are ways of viewing string theory which has nothing to do with string theory. It's just quantum mechanics. And I think that's very important, that this whole, it's not some absolutely bizarre structure that people with large egos invented and then stole all the government money, which is how this is sometimes portrayed. That's not the case. It's a very natural extension of things that we know work, and it fits into this picture. And some aspects of even this new extended theory of string theory are just the way they used to be. It's just quantum mechanics. Okay. So I think it's important to keep this in mind. And I think this is why the field keeps going.
Okay.
Yeah.
Okay, maybe just a bit to finalize. What are the questions that concern you the most at the moment? What is your current resume? Maybe in a bit more specific. Is there one particular question that is motivating you now, or there were some problem that you're working at the moment?
Yeah, well, I always work on many things, as I think do all scientists. I I rarely work on only one thing.
Okay.
Well, I don't know. I'm interested in various things. One thing that I'm interested in, which has absolutely nothing to do with string theory, is plasma physics.
Okay.
So basically, but actually, again, through techniques that we learned, we learned how to phrase plasma physics in the language of string fluids.
Okay.
So you can think of plasmas as fluids where the strings are the magnetic fluxes, and they flow like strings. There's nothing to do with string theory. It's just the mathematical structure is there.
Okay, cool.
So we have some new predictions there, actually, for how plasmas, let's say, inside of neutron stars, maybe even inside of quark-gluon. Inside of CERN. This is called quark-gluon plasma. We have a new kind of mathematical framework to address questions which I believe are outside of what people used to be able to do. So that is something that I'm quite interested in, because it's actually it may be experimentally verifiable, and everyone likes that. So I like this. I'm also interested in some more fundamental questions about this duality. I'm interested in certain measures of quantum chaos which have not been understood yet. For example, these chaotic entropies, how they behave, because one nice thing about this duality is that essentially what you've learned is that everything you can ask that's geometrical about gravity, because gravity is a geometrical theory, it has some incarnation in quantum mechanics, and vice versa. So therefore, every concept that people have addressed in quantum mechanics, there should be some gravitational incarnation of this. So there are some specific things which I'm interested in, which have to do with classification of quantum chaos, which I would like to understand better. So that's something I'm working on. Then there are these various practical things about transport, some aspects of transport coming. What is the mathematical structure of fluid dynamics? What is the mathematical structure of fluid dynamics with other more short-lived modes, things like this. I'm quite interested in these mathematical aspects of transport theories. Again, also in mathematical aspects of chaos. And through all of this, string theory gives you toy models, which you can use to actually do something and learn, hopefully what you learn is general enough so that, it's also applicable to the actual universe in which we live. So there are these various aspects of things I do right now.
But I find very cool that it's quite diverse. You try to explore several areas.
Yes.
I was skimming through your papers, and I actually find a bit surprising that's one of the words that I think appears the most, at least lately, is hydrodynamics, that maybe is not something that you relate to string theory or to theoretical physics. Well, maybe in theoretical physics, yes, but not particularly to string theory or something like that.
Yeah, but it's exactly through string theory that in the last few decades, there's been a rebirth of growth, of rebirth also of interest in hydrodynamics. People used to think that, everything to do with hydrodynamics was resolved in the 19th century. There are these Navier-Stokes equations. If you can solve them, you'll get $1 million, and that's it. But it was actually, again, through this AdS CFT correspondence, that people learned that there's much more to hydrodynamics. There are higher corrections to the old story. There are quantum corrections to the old story. Then something I've worked on as well. So I've worked on various these things. There's also, for example, formulation of hydrodynamics in the language of field theory is something that has now been only understood by people who are string theorists. So, again, this way of generalized mathematical way of looking at theories in a unified language has been extremely helpful. So yes, I'm genuinely interested in hydrodynamics, and hydrodynamics, is this, but it's not only this; it's also the motion of collective states inside of CERN. There are these things called the quark-gluon plasma, where you collide two nuclei, and there's a ball of fundamental particles created, which behaves like a fluid.
Okay. Maybe just to clear it up, because I think most people are familiar with the three states of matter, liquid, gas, solid. Just maybe you could briefly define what is a plasma?
What is a plasma? Traditionally defined, I guess, or maybe the only way to define it's like gas, where but the constituents are electrically charged. Okay. So the normal way you achieve this is that you take gas and you heat it up even more, and you break the bonds inside of atoms. So basically, so you have positively and negatively charged particles. So it still behaves kind of like a gas, like a fluid, but because things are charged, they also interact electromagnetically. So it's like a fluid where the electromagnetic force plays an essential role for the dynamics of the whole thing. Okay, so of course, in water, the electromagnetic force is essential inside of the H2O, right? It keeps it together. But the actual motion of the molecules themselves isn't particularly influenced by magnetic field or electric field. In a plasma, there are very strong magnetic fields, and you can also induce strong electric fields, and they're important for the collective behavior of the whole thing. So the solar corona is a plasma, neutron stars are a plasma, these things at CERN are a plasma. I don't know, things that they try to use to make fusion are plasmas, which are, very, very hot gases that you can put in a magnetic field and they interact electromagnetically. So that's a plasma. So it's a general state of matter which doesn't fit into any of those three. That I've been very interested in. Yeah, and I would say that string theory has been helpful in a way for us to think about these things.
Okay, so good. Another example of how string theory has helped our understanding of the universe or some aspect of the universe. Okay. Okay, so honestly, I think that's it. But thank you very much for accepting. And honestly, it was very interesting to talk about this. I also work in physics, but I have never studied string theory formally. I'm very fascinated by it. I think one of the most fascinating areas in physics, I would say, you see the amount of documentaries in science, a lot of them are string theory, are about string theory because it was very fascinating and the question that it tackles. So thank you very much.
Thank you. Thanks for the invitation and this nice chat. Thank you.
Okay, I think that's it. Okay, so honestly, I think it was really good. So thank you very much.
I hope.